Today, let's talk about the normal distribution with mu is equal to 0 and sigma is equals 1, which is known as the standard normal distribution. It is one of the most commonly used probability distribution in statistics, and it is central to many statistical tests and methods. So the properties of this standard normal distribution is first, the mean mu is 0, and the standard deviation sigma is 1, and the probability density function of this standard normal distribution is f of x equals 1 over the square root of 2 pi times e to the negative x squared over 2. So this distribution is symmetric around the mean, which is about 68% of the data falls in with one standard deviation of the mean, and about 95 of them falls within 2 standard deviation, and nearly all, which is 99.7% of them, falls within 3 standard deviations. Let's look at some example of calculating the probability density function for different values of x to see how the probability density changes. So first, f of x is equals 0, which is equals 1 over the square root of 2 pi times e to the negative 0 squared over 2, which is equals 1 over square root of 2 pi, which is approximately 0.3989. So this is the peak of this distribution since x is equal to the mean mu. When x is equals to 1 or x is equals to negative 1, they have one standard deviation from the mean, which is f of 1 equals 1 over the square root of 2 pi times e to the negative 1/2, approximately 0.2420, which is f of negative 1 equals f of positive 1, which is also approximately 0.2420. So this density is lower further from the mean, which reflected the lower probability of values from further from 0. When x is equals to or negative 2, they have 2 standard deviations from the mean, which is f of negative 2 equals f of 2 equals 1 over the square root of 2 pi times e to the negative half of 2 squared, which is approximately 0.05399. And when x is equals 3 or negative 3, they have 3 standard deviations from the mean, which is f of negative 3 equals f of 3 equals 1 over the square root of 2 pi times e to the negative half of 3 squared, which is approximately 0.00443. So this example shows how the probability density decreases as x moves away from the mean, which reflecting the characteristic of bell curve shape of this normal distribution. Let's talk about the formula of probability density function of normal distribution, which is g of x mu sigma equals 1 over the square root of 2 pi sigma squared times e to the negative x minus mu squared over 2 sigma squared. So mu is the mean or expectation of this distribution, and it is also median and mode, and it determines the location of the center of the peak of this distribution. And sigma is the standard deviation of this distribution. It measures the amount of dispersion or variability. So a higher sigma indicates a wider spread of the values around the mean. Sigma squared is the variance of this distribution, and x is the variable of this function in the context of probability. It represents a value of the random variable whose probability density is being calculated. So 1 over the square root of 2 pi sigma squared is the normalizing factor that ensures the total area under the density curve equals 1, which making it a proper probability distribution, and the square root of 2 pi sigma squared. In this denominator, it is derived from the integral of the exponential function, which balances the equation to maintain the probability properties. So e to the negative x minus mu squared over 2 sigma squared is the exponential function that gives us this distribution is characteristic symmetric bell-shaped curve, which is centered at mu and decreasing as x moves away from the mu, and the exponent negative x minus mu squared over 2 sigma squared is the quadratic function in x, which indicating how improbable it is to observe an extreme value as x deviates farther from mu.